Young, A period Peter Young, speaking on states, metastates, and replica symmetry breaking with a long subtitle that he will explain.
Thank you very much, and thank you to the organizers for inviting me to this interesting meeting and giving me the opportunity to visit again the Eternal City. It's been very nice to meet some old friends here from the past, and even nicer actually to see a lot of young scientists here who are interested in the topic of this meeting. So what I will be talking about really is the, oh dear, what did I do? Made a mistake. The subtitle here, which is whether there is a static description for spin glasses which is related, which gives information on what you can actually observe experimentally, which is dynamics. Now this is work done in collaboration with Matt Whitman. As you see, it's not very new work, but I believe it fits in with the topic of this conference. Let's see if I can get that right. So in experiments, you measure at different times, you do a time average. But theoretically, it's much more convenient to compute static averages for the Gibbs distribution. And it's a tenet of equilibrium statistical physics that normally these two agree. But of course, there are exceptions. So one exception is a system with a phase transition. So the simplest example, which we all consider, the Ising ferromagnet, which in experiment below TC, it's either in the upspin state or it's in the downspin state. And these up and downspin states are what's called in the trade pure states. Pure states which have a very convenient property, clustering property, which says that the correlations basically go to zero at large distances. So Ri minus Rj goes to infinity. The average of the product of two spins SISJ is the same as the product of the averages. So this is a convenient property, this clustering. However, if we just do the Gibbs average, then we include with equal weight the upspin state and the downspin state. And if you do that, then each individual spin has zero average, whereas the product of the two spins at large distances does not. It will go to something like the magnetization squared. So you do not have a clustering property if you just do the Gibbs average and don't do anything to break the symmetry like applying a magnetic field. So this is called a mixed state, mixed states which do not have this clustering property. So this is, of course, the simple example which we're all familiar with, but the topic, or one of the major topics of this meeting is, okay, I am struggling here to do this. Right. So the clustering property is convenient, so how can we describe spin glasses in terms of pure states? So this has been extensively discussed in many papers by Newman and Stein. So first of all, how do we define a state and see whether it's a mixed state or a pure state? Well, what we have to do is look at the set of correlation functions in some finite region here, and we look to see if these correlations have the clustering property or not. And the problem is complicated in spin glasses because you can have different pure states which are not related by symmetry. So how can we characterize them? Now, as I understand it, the notion of pure states can be defined rigorously only in the thermodynamic limit. But what we would really like to do is to have some limiting process where we take a large but finite system and let the size get bigger and bigger without having to take the thermodynamic limit in the first place. So in the Newman and Stein picture, you consider a region in the center with a certain set of interactions, and then you grow the system more and more. You add more and more interactions, keeping those in the middle the same, and you see what happens to the state of the system in the middle. And the situation is complicated by the fact that as you grow the system, the state in the middle can vary, possibly chaotically, as you add more and more bonds. So this chaotic size dependence, is one of the major predictions of the or contributions of Newman and Stein. So we need to have some sort of description in terms of the distribution of all the states that you generate as you make the system bigger and bigger and bigger. And this distribution of these states is called by Newman and Stein the metastate.
Excuse me, Peter.
Yes.
There are several ways you can enlarge your system. Okay? Because you have random terms, so you have several realizations, so you can consider many larger systems with different values. So how this problem is handled?
Well, I'm actually, in practice, going to use a somewhat different and I think much simpler, both for me conceptually and also numerically, definition of the metastates due to Eisenman and Ware. So I'd rather confine my attention now to this definition, and afterwards we can chat about the point that you raised. So what Eisen and Ware do is argued by Reed in particular, who's here, to be equivalent to the Newman and Stein metastate. And I will now explain what that is. So we have a large system of size L with, say, periodic boundary conditions. And we're going to consider correlations in a small region, a window size W in the middle. And then there's an intermediate scale, which I'm now going to call M, which has the following situation. So W is much less than M, is much less than L. And eventually, all these scales will go to infinity. So what we're going to do is, for a given set of interactions everywhere, we're going to do the Gibbs average for a given set of interactions. And we look at the state in the window. It may be a pure state, in which case it would be clustering. It may be a mixed state, in which case you would not have clustering. And then we generate this metastate by repeating for many choices of the interactions in the outer shaded region. That scales between M and L. And finally, you can average over the bonds in the inner region, which is supposed to be not, strictly speaking, necessary in the limit W goes to infinity, but numerically you would certainly want to do that. And then we're going to calculate what is called the metastate average state, MAS. So it's important to understand what this means. So the angular brackets, SISJ average, that's the standard Gibbs average. And then this rectangular brackets with the outer means average over the bonds in this outer shaded region. And you will notice the square is only done right at the end. So we compute a correlation between a pair of spins here, simultaneously doing the thermal average for a given set of bonds and averaging over the bonds in the outer region. So it's important to understand the square there. So we hear about different scenarios for the state of spin glasses. What would they predict for this Eisenman-Ware metastate? Well, one possibility is that for each set of bonds in the outer region, the window is in a pure state, as determined by the correlations being clustering. And furthermore, as you change the bonds in the outer region, you get the same pure state in the central region. And this is my understanding of the droplet model of Fisher and Hughes, and there was related scaling theory by Bray and Moore and by Bill McMillan. Another possibility is for each set of bonds in the outer region, the state in the window is in a pure state. But when you change the bonds in the outer region, this state varies chaotically. And this is the chaotic pairs picture of Newman and Stein. A third possibility is that for each set of bonds in the outer region, the window is in a mixed state. And furthermore, this mixed state itself varies chaotically when varying the bonds in the outer region. And this is the replica symmetry breaking picture of Parisi. So some comments. I'm only going to be working in zero field. So of course there's always a pair of states related by spin inversion symmetry. So when I say pure state, I really mean a pair of pure states related by time reversal. Now, in the droplet model, the state of the system then in a local region here doesn't depend on what the bonds are very far away. Whereas in the chaotic pairs and replica symmetry breaking, the state of the system in this local region does depend on the set of all far away bonds. And I imagine that would make the calculation of the ground state much harder, because you can't really just get the right answer by locally optimizing different regions and then trying to paste together. What are the various predictions then in these three scenarios for these mass correlation, which is the spin-spin correlation function averaged also over the bonds in the outer region? Well, for the big droplet picture, you just get the square at large distances, you just get the square of the order parameter q. Because you have clustering, because it's by hypothesis in a pure state, this quantity just becomes q squared, and the average over the outer bonds really doesn't do anything, because by hypothesis, you're getting the same state for each set of the bonds. In the chaotic pairs picture, this has been worked out by Nick Reed, who argues that the correlations actually fall off with a power law distance to the minus d minus zeta for some value of zeta. And the one we're going to mostly focus on, the replica symmetry breaking picture, you also get a power law, and according to Reed, the exponent zeta is equal to 4 in mean field theory, which means d bigger than 6. This 4 comes from some work of de Dominicis and Condor on the fluctuations about the Parisi solution. And actually the same result, but for a slightly different quantity, was also obtained by Marianari et al. And they computed, looking at two replicas, they computed the correlations between the two replicas in the so-called Q equals 0 sector, where there's no overlap between the zero overlap between the spins in the two copies. Perhaps that is the same thing as this mass average. Certainly in mean field theory, the prediction is the same. So the mass correlations were computed in 3D by Bilwao et al. That was also mentioned in the talk this morning by Juan Luis Lorenzo. And they found that zeta is less than d, so the correlations fall off, which suggests RSB or chaotic pairs. So far, we've talked about statics. Now, the goal of this talk is maybe to connect statics and dynamics. So now we focus on dynamics. And we suppose we do the usual thing. That is, we quench the system below TC and watch it evolve. It will evolve slowly with time. It will never fully equilibrate because the spectrum of relaxation times goes off to infinity for a spin glass. But there's some distance, some scale, psi, which will depend on t, up to which the system is locally equilibrated. And psi of t only increases slowly with time. It's found empirically in simulations to be a power of t written as 1 over z. Z, the power depends on temperature. and is a sort of a non-equilibrium dynamical exponent. Now z is often quite big, and 1 over z is quite small, so maybe it's not so easy to distinguish this from a logarithmic dependence, but the numeric seems to be fitting better with a power law. So then the question is, how does this, so then we compute the correlation function between the spins. It's similar to the previous definition. It's SISJ, but now it's at a time t. And we now thermally average it. This is just what we usually do before we average over the disorder. The average over the disorder is this rectangular bracket, and this is now over all the bonds. We're not anymore having these different scales. At distances less than the correlation length, one observes a power law. So a natural hypothesis is that the correlation length depends on 1 over the a power law of distance, 1 over the distance to some power, which I'll call alpha d, d for dynamic, times some function of the distance over this time-dependent correlation length. So if we wait a fairly long time, so the correlation length is bigger than the distance, then presumably this scaling function just goes to a constant, it's f of 0, and so we get a power law, 1 over r to the alpha dynamic, alpha d, when the distance is small compared with the correlation length. And this is somewhat analogous to what we got from the mass averages, where there was 1 over r to some power, which I'll now call alpha s, s for static. And in mean field theory, and I should have also indicated within the replica symmetry breaking, alpha s is d minus 4, at least for d bigger than 6, because that's the mean field prediction. So we have two results there that look similar in the sense that they're both power laws. So let's look again at this figure here with our 3 scales. We have a very big system L, and we have a window W. And let's supposing then we now consider the non-equilibrium behavior where there's a correlation length psi of t, and let's assume that it's grown to a size bigger than the window. So what I was calling m in the static case, let me call this psi of t in the time-dependent case. So there's actually, you see there's some sort of similarity between this static metastate and what I'm calling the dynamic metastate. And actually this similarity was first pointed out by Daniel Fisher, who's here, and Olivia White, who used the term maturation metastate to describe the ensemble of states generated dynamically by the fluctuations in the spins at large distances which are not equilibrated. So in some loose sense, the effects of averaging the exterior bonds in the static metastate, MAS average, are perhaps analogous to averaging over the non-equilibrated fluctuating spins in the dynamical measurement at scales of order bigger than the correlation length. So there seems to be, at least to some extent, an analogy between psi of t, the time-dependent correlation length, and this intermediate scale m in the Eisenman-Ware metastate. So both in the Eisenman-Ware metastate, correlations go off like 1 over r to alpha s. In the time-dependent non-equilibrium, 1 over r to the alpha d. And the question we're going to discuss is whether alpha s is equal to alpha d. That will be the question we'll be addressing for the rest of the talk. If so, it would clearly be useful to establish a connection between statics and dynamics, because statics is easier to calculate than dynamics. Okay, so in 2010, Alvarez Baños et al. Looked in 3 dimensions and found numerically that the dynamic alpha d is close to a quantity, this fall off of correlations in the zero overlap sector, and which is presumably similar to a mass average. So therefore, what they found was that alpha d was similar to a quantity very analogous to alpha s.
But how convincingly? So here you're assuming that it's a power law and asking for whether they're equal. But how convincingly is it that it's a power law?
Are you talking about 3D, which is not my main focus, or the mean field, which is... Well, okay, so for the mass average, Nick Reed calculated it analytically and found a power law. And numerically, on the time-dependent average, I'm going to show you some data which plausibly looks like a power law. And you can decide if you think it's... And this is 3D, yes. So maybe some of the authors, I'm sure, are here, so we should perhaps ask them about that. So I'm going to focus on the mean field limit because of this analytic value for alpha s. We know it's a power law for the static case analytically, and the power is d minus 4 because Nick Reed worked it out. So what I would like to do is, since we have this anchor point, d minus 4, I want to determine the dynamic equivalent for d bigger than 6 to see if it's the same. Now this is not easy to do numerically because the number of spins, n, increases too fast with L. N equals L to the d. So instead, what we did was we investigated a model in one dimension with long-range power law interactions. And there's been quite a number of papers arguing that these, to some reasonable extent, can be a proxy for a short-range model in d dimensions. And varying the power in the long-range model is equivalent to varying the dimension in the corresponding short-range model. Of course, in one dimension with short-range interactions, we know there's no transition, but with long-range power law interactions, then there can be. So the Hamiltonian is given by the usual expression, Jij, Ising spins. The bonds are independent random variables with zero mean and a variance which falls off like 1 over r to the 2 sigma. So sigma is the power. So the simple way of doing that would be to have every spin interacting with every other spin with a strength which falls off like 1 over r to the sigma. But this is very inefficient. As we heard in the talk from Majorano this morning, this means that if you want to update a spin, you need n operations to calculate the field. So to do a sweep, it needs n squared operations. So we'll follow instead the smart ideas of Liuzzi et al. And consider a dilute long-range model. So in this model, most of the bonds are not there. The probability that the bond is there falls off with the power of the distance. And if it is there, it's of strength 1. So we get this Jij. What happened to... Yeah. So we get this mean square falling off like 1 over r to the distance, not by making the strength fall off with distance, but by making the probability that you get a non-zero bond fall off with distance, like 1 over r to the 2 sigma. So in this way, you can choose a mean coordination number. We chose it to be 6. And this is much more efficient. For example, we've needed to do large sizes up to n equals 2 to the 26. So for the non-dilute model, you need about n squared operations to do one sweep for one sample. That's about 4 times 10 to the 15 operations per sweep. This is a big computer effort, even now, to do one sweep. Whereas for the dilute model, it's of order the number of neighbors, which we choose to be 6, ZB times n. That's about 4 times 10 to the 8. And this is manageable. That's about a gain of about a factor of 10 to the 7 by using the dilute model rather than the model where everything interacts with everything else. And we do 1,000 samples for each size. So maybe I need to move along here. We choose a model corresponding to d equals 8. And I don't have time to really go into details. The relation in the mean field limit between sigma of the long-range model and d of the short-range model is given by this. So the long and short of it is we choose sigma equals 5/8. So what about alpha S? Well, the whole point about this relationship between models is that there's a correspondence between the exponents. And because one of them is in d dimensions and the other is in 1 dimension, it turns out the exponent for the short-range model is d times the exponent for the corresponding long-range model. So for the long-range model, the metastate alpha S is not d minus 4, it's d minus 4 over d, and we have a sigma corresponding to d equals 8, so that's 1/2. So alpha S is 1/2 for our model. Is alpha D 1/2? That's the question we're going to try to ask numerically. So in the numerics, we quench the system to 0.4 Tc, well below Tc, in order that we get, should be not troubled by critical fluctuations. Sizes up to 2 to the 26, times up to 2 to the 14. Now, this is a plot of the correlation function. It depends on r, ij, it depends on t, plotted as a function of r, ij at a fixed time. This is the longest time we took, 2 to the 14, and the different data is for different sizes, from 2 to the 10 to 2 to the 26. So you see there's big finite size effects, but the last 3 points, 2 to the 22, 24, and 26, all agree nicely, even at this longest time. So the data for the largest sizes seem to have converged. So this is really the main numerical data of the talk. This is now focusing on the largest size, 2 to the 26, and the correlation function is plotted as a function of distance now, and then for different times. So the shortest time, 2 to the 4th, is red. The longest time, 2 to the 14, is this cyan color. And what you can see is a crossover. Looks like this is a log-log plot, so it looks like a crossover between 2 power laws. If you look at the longest time for which the correlation length has grown to the biggest amount, at short distances, the slope corresponds to this dash curve, which has a slope -0.5, which is the same as the dynamical alpha. So this at long times, presumably in short distances, we're in the region where r is less than psi over t. So numerically, that's the same as the mass average. If you cross over to larger distances and shorter times, it's close to this dashed line, which has a slope -2 sigma, and this is due to the fact we have long-range interactions. Normally, the correlation length at large distances longer than the correlation would go off exponentially, but we have a long-range coupling, so there's a direct coupling between here and there, and since this is the correlation length squared, that falls off like the average interaction squared, and that's why there's this -2 sigma. So we...
Just to understand the length, so your system is total length is 2 to the 26.
Yes.
It's a very small fraction of the total length showing the data.
That's right. Yes.
It extrapolates out to those continue down the way they look?
Yes. Yeah. Yes, that's right. Yeah, it continues down. I mean, to show the crossover, I didn't produce the data all the way out to 2 to the 26, but it does continue down in this way. So this is the main result. Here we've done some sort of fit to the data, to the slope of the data. This is the slope of the data as a function of r, trying to extrapolate back. And this is short time, this is long time. And the data seems to be extrapolating to a value close to -0.5. And of course, I'm not saying it's exactly -0.5, but it seems to be reasonably close numerically. And I think that's just a scaling plot. My time is out. I'm going to skip that. So we'll just conclude that we've investigated in the mean field region a possible connection between the dynamical and static metastates. We took a long-range model corresponding to a short-range model in d equals 8, which is above the upper critical dimension. And the averaging over the nonlinear dynamics within the numerics gives the same power law behavior with r as the metastate average computed by Reed, assuming replica symmetry breaking. And the more general question then is, are the static and dynamics metastates equivalent quite generally? I don't know what the answer is to that. It would be good to have some more intuition. And with that, I'd like to thank you for your attention.
Questions?
Could we see data graphs? Could we see the data graphs?
Yes, this is the data collapse. And this is for a particular value. So I took here psi of t equals t to the 1 over z. I assumed a pure power law, and I got the decent data collapse with z about 1.4.
So there are constructions for the
Yeah.
there are constructions for the metastate in systems with long-range interactions.
Was that a question or a
The
statement?
question, no, it's a
I don't know how
there.
I don't know how I would do that, because I have to define an inside and an outside, and if everything is coupled to everything else, I'm not sure that I would know how to do that. But there may be some scheme for doing it, but I don't know what that would be.
You said to understand this question in other dimensions, maybe closer to our own three, you need more intuition. But did you just, why did you not just run with different values of sigma and look at the answers?
Well, it's really a question of mainly computer time, also human time. For the level of computing we had available, this was fairly big computing for us. It would not be big computing for Rome, as we heard this morning in the talk by Majorano. So we thought it was better to do as good a job as we could with available computer time on the one value of sigma, rather than do a less good job for different values. But it would be, I'm certainly agree, it would be interesting to do others. There's no barrier. I mean, what I wanted to do was have an anchor point of that analytical result. So I wanted to be in the mean field region. Otherwise, there's two results, both of which are obtained from numerics, and it increases the uncertainty. Where one is obtained analytically, I thought that was useful to compare with.
So just a couple of comments. So one thing about the scaling with time. So I think that if there is a stiffness in the system which grows with scale, you can't get power of time. It's going to definitely be logarithmic. And so that's raises a question of whether you're sort of in asymptotic regimes. But the other one, which is a question which is connected to something I asked this morning, which is a question of the convergence to the mean field. So this, because the way you've done this, the lattice, was very dilute,
yes.
Presumably it's very tree-like. If I look at the coordinations and I look at how things connect together, and with rather large loops and sort of not having small loops except very locally. So is it, I guess I don't quite see why I wouldn't sort of expect it to converge to something that was more like a beta lattice, where there are different behaviors presumably for these dynamical and static quantities.
Well, in beta lattice, there is no notion really of distance.
Yeah,
No,
but I have
I'm
to
not
look at
saying
how
that.
tree-like this is, right? That's the, if I, yeah, but that doesn't,
Yes, I mean, I have
it can be above the
six-
percolation list and still we have very large loops, right?
It can be large loop, but I have 6 neighbors, so it's definitely a percolating system.
Yeah, but that doesn't matter. I mean, I can,
Well,
If you take Katz interactions with variable range of interactions, and that you let this range of interactions with infinity be compared to the
yeah, that's different.
I think we've reached the point of discussion, and let's thank the speaker.